So our next problem here deals with writing electron configurations of some main group ions. So we're going to kind of do some things that were very similar to what we saw in sample problem 8.2 when we wrote electron configurations. We're not going to do partial orbital diagrams here, and we're only going to write condensed electron configurations. But now we're going to consider formation of ions. And so this kind of brings back some material that we learned about in chapter 2, which was, okay, look at this atom. Tell me what it's going to be when it makes an ion. So, for example, if we look at the first atom here, iodine, right? If you don't remember some of these, you always have your periodic table. It's your best cheat sheet. Iodine here, if iodine becomes an ion, in order to have a full octet, iodine's going to gain 1 electron and become I-, okay? And so this problem is actually asking us to think about electron configurations in the context of using them as though we are making ions and writing equations for that. Okay, so we can represent iodine as, go to the previous noble gas, right? So if we look at iodine, the previous noble gas is going to be krypton, okay? And so we're going to write krypton. Oh, let me keep our periodic table here. So we've got krypton, and then we go 5s2, 4d10, 5p, 1, 2, 3, 4, 5. 5p5 will get us to iodine. So again, let's write that down. We've got 5s2, 4d10, 5p5. Now, iodine wants to become an anion. And so to become an anion, that means you need to gain, in this case, it's in group 7, so it's going to gain 1 electron, and it becomes I-. So if we were to write the condensed electron configuration for I-, again, it's going to be krypton, 5s2, 4d10, 5p6. Well, really what we've done here now is we've written the same as the electron configuration for xenon, okay? Not surprisingly, iodine wants to gain 1 electrons to have the electron configuration of xenon, its closest noble gas. So again, we would say that this is isoelectronic with this, okay? Next example here, potassium. Right? You probably already can see the trend here and how this problem is different. We're going to be making a cation. So potassium here, if we look at potassium on the periodic table, go to the previous noble gas. We've actually already written the electron configuration for potassium. So it's argon and then 4s1. So potassium, we can write argon and then 4s1. We showed anion formation as the gaining of electrons. So cation formation is going to be the loss of electrons. So making K+, again, isoelectronic with argon. That's the noble gas it got to become. And again, losing 1 electron. All right, our next example here is indium. Okay, and so the trend and how we become different from the previous problems that we've done is indium is a transition metal. And you might remember when we started learning to name things in chapter 2, one of the things that we learned is that transition metals often have multiple oxidation states or multiple charges that they could be. So again, we're just going to write a little note here. We can have multiple options for what we can become as an ion for indium. So let's just start with one of them here. Again, if we're going to write the condensed electron configuration for indium, again, indium is atomic number 49, so it's right here. So we go to the previous noble gas, which is krypton, and then we're going to have 5s2, 4d10, 5p1. Okay, so that's going to be the electron configuration of indium as an atom. So krypton, 5s2, 4d10, 5p1. Well, you might not know this, but here are the 2 possible options for indium. Indium can be a +1 or a +3 cation. So let's take the +1 example first. So again, we're going to be losing electrons to become cationic, but if we make the indium +1 cation, we have to think about where that 1 electron must have come from. Well, hopefully it makes sense that we're going to get rid of this single p electron, because then the s orbital is still filled with 2 electrons and the d orbital is still filled with 10 electrons. So again, that's going to be krypton plus 5s2. So that 5s2 is still filled, and then 4d10, and then we've lost an electron. Going through the other example, again, we can have the same indium, making indium +3. So if we had to lose 3 electrons, hopefully the logic makes sense that we're still going to lose this p electron, and now we'll lose these s electrons, and that leaves these d electrons untouched and that orbital filled. So again, we're going to have krypton here, 5s2, oops, I'm sorry, we just took those away, krypton, and then after taking the 5s2 electrons away and the 5p1 electron away, we're going to have 4d10, and in this case we've lost 3 electrons. So again, a couple of things that we kind of brought into play here. We had to remember from chapter 2, what are these atoms going to want to do when they become cations or anions? And then using kind of in mapping on new information was writing electron configurations both for the starting atom as well as the resultant ion. And remembering that things happen because these atoms want to become isoelectronic with noble gases.